Okay, so let me review the Dirac algebra and the spinors and charge conjugation and parity. I found a nicer way to do all this. It's again using that trick that I showed you. Let me just mention what Weinberg's approach is. He wants U of LA. This is a unitary transformation that implements a Poincare transformation, which in this case is a Lorentz transformation followed by a translation. And he wants that on some psi L of x, U inverse of L and A, to be a sum on L prime of some representation of the Lorentz group at L inverse psi L prime of Lx plus A. Okay, that's the basic requirement of Lorentz invariance. The other requirement is that either the commutator or the anti-commutator should vanish at space-like separation. So this is x minus x prime squared less than 0 in Schwarz's metric. Now, Weinberg proceeds from here, and as I said, I think that's the gold standard, and my treatment is a basic one. Let us call it the iron standard. I thought maybe copper or iron, but I decided maybe iron was better. All right, in any event, you remember that if phi is any four-component object that satisfies the Klein-Gordon equation, then this combination, I d mu gamma mu plus m on, let us say, AB on phi b of x, this satisfies the Dirac equation, which is, of course, I d mu gamma mu, minus m psi of x equals 0. And now that some of you have told me where to find a LaTeX package for slashes, I'm happily using that. For those of you who don't remember, the lesson is use package cancel, and then you just do backslash cancel, and then whatever it is in squiggles, curly, I don't know what you call them. Anyway, the usual thing. Okay. And so, we of course are going to be expanding psi as the sum over the spins minus the plus integral d cubed p 2 pi cubed. Some of this is repetitive, but I'm going to actually put in an extra index n here. And this n means the kind. So one kind would be electron, another kind would be up quark, another kind would be down quark, or strange quark, top quark, whatever. And then we have V of P and S. Well, in this notation, then we have a dagger of PS NC e to the I px. NC means the conjugate. So in other words, if N is electron, NC is positron. If n is up quark, NC is anti-up quark. Or if n, yes.
Why don't we have B?
Hold on, let me give you, let me find the candy. What was that?
Why don't we have B dagger?
P vector?
B dagger in the place of A dagger.
Ah, brilliant question. That's great that you make that observation. That is slightly anomalous. Oh, how can I say? It just isn't V star. It just is V. In other words, we're going to have two spinors so that this satisfies Dirac's equation. I mean, you could call it V star if you want.
I'm not talking about B star, I'm talking about B. Bravo.
B. Oh, B as in. Well, because what I wanted to do was adopt a somewhat more general notation where this, in other words, we previously had B dagger. That was where B dagger creates the positron. Now this thing creates the antiparticle. That's Weinberg's notation, and it sounds a bit heavy in the beginning, but when you actually are playing with things, it turns out to be better. So evidently, if we set U equal to I d mu plus m on any four-component object U0 e to the minus I px, we'll have a solution of Dirac's equation. And this thing turns out to be P mu gamma mu plus m on U0 e to the minus I px. And of course, you can write that as P slash. And just to recall, the gamma matrices that we're going to be using look like this. Okay, so those are the gamma matrices. And so U of P and S then is P slash plus M on something or other. And that would be some U0 at, or I should say proportional. The proportionality factor could depend upon the energy. And what we do then is we ask, well, what is, let me just call it U0 of S, because of the normalization issue. So then U0 of S is M gamma 0 plus M on this U0 of S, and so this is basically MM, well, this is kind of silly, isn't it? Let me, we're short here over, oh, here's an eraser. Let me just write this M 1111 0 of S. And of course we can set U0 of S equal to some arbitrary two arbitrary 2 vectors. And then you see that we find that U0 of S is M, and now this is going to be C plus zeta, C plus zeta. And what that means then is that this is M alpha of S, alpha of S. In other words, the upper 2 spinor has to be the same as the lower 2 spinor. Okay. Now, there's some arbitrariness of an overall phase, but you can always choose the phase so that alpha plus is 1, 0, and alpha minus is 0, 1. And so the spinors at 0 momentum are the up spinor, it turns out to be square root of M 1, 0, 1, 0, and u 0 minus the square root of m 0, 1, 0, 1. Okay. Now, you can then compute what they are for arbitrary p just by multiplying by p slash plus m with the appropriate normalization. And so in fact, what we can say is that u of p and s is, I think it's nicer to write m plus p slash, and it's over square root of 2 p plus m. So this is Schwarz's normalization. And then this would be alpha of s, alpha of s. So these are the formulas for spinors. And in the PDF I sent you, I worked out the exact form. In fact, let me show you what it is. I'll just skip the actual intervening steps, although well, I was going to say they're easier this way. I'm not sure they are. But anyway, here's what it looks like. It's m plus e minus p3 minus p1 minus I p2 m plus e plus p3 p1 plus I p2. And you remember, I was a little puzzled by this because if you have a what was I thinking of? You have some cancellation here if it's moving in the z direction. And in fact, let's suppose we go to the massless limit. So as m goes to 0, what does this turn into? Well, it turns into 1 over the square root of 2e, but then up here it's 0. Now let's suppose it's moving in the z direction, which of course by state law is up. So then e and p3 are the same, so this is actually 0. p1 and p2 are 0. But here this is 2e, and then 0. So what is this saying? This is saying that if the particle is moving in the z direction and has spin up, which is, let's see, that is the general. This is u of p plus. So this is the spin up. Then the left-handed spinner is 0, and only the right-handed spinner can have can be spin up. Okay. And similarly, u of p and minus is, of course, m plus p slash square root of 2 e plus m, and now this would be 0, 1, 0, 1, and what you get is 1 over the square root of 2 e plus m, and now minus p1 minus plus I p2 m plus e plus p3 p1 minus I p2 e minus p3 plus m. Now if we again take them m equals 0 limit, we get 1 over square root of 2e, and then we get 0, 2e, 0, 0. So now it's the left-handed particle that can have spin down. So the left hand is the upper two components, the right hand is the lower two components. So the left-handed spinner can have spin down and move in the state-approved C direction. All right, now for antiparticles, it's the same business. We just set V equal to I d mu plus m V0. But now the phase has a minus sign in it, or equivalently a plus sign in this case. So V is I d mu gamma mu plus M. There's a typo. V0 e to the I px, and so this is M minus P slash, effectively, V0 e to the I px. All right. So now V of 0 and S then would be M minus M gamma 0 on some V0. And so this is M1 minus 1 minus 1, 1 on some C zeta, let us say. But then this turns out to be M C minus zeta, zeta minus C. So we can call this M beta minus beta. And the important thing is the minus sign here. Now, the lower spinor, in other words, for the antiparticles, the lower spinor is the negative of the upper spinor. But the spin up one is beta plus, has to be 0, 1, and beta minus is then minus 1, 0. And so then, so this is different. I mean, Schwartz just, I'm afraid, got it wrong. V0 plus then, the 0 momentum spin is then square root of M 0, 1, 0 minus 1, and V0 minus square root of M minus 1, 0, 1, 0. Now, you might say, well, where did I get this? Well, of course, I got this from Weinberg. Where did Weinberg not get it? Well, Weinberg got it by very carefully arguing through applying both Lorentz invariants and the requirement of the fields, either commute or anti-commute space-like separations. That forces this choice, apart from an arbitrary choice of phase, which would say, well, you want the alphas to be simple 1, 0, and 0, 1, rather than some crazy phase. Once you've done that, you're basically forced into this. And okay, so what do the spinors look like then? V of P plus then is M minus P slash. Remember, M minus P slash over the same normalization, square root of 2 E plus M, and now it's beta plus. In fact, I could have said just beta plus and minus. Is beta plus and minus minus beta plus and minus. So it looks like that. So that's the rule there. Okay, so these are our general spinor formulas. I could write them down. In fact, I did write them down explicitly, and I guess we might as well take the massless limit just on the fly here. So what is V of P plus in the M goes to 0 limit? Well, it's 1 over square root of 2E, and it's going to be 0, 2E, 0, 0. Do I have that right? Yes. And V of P in minus 1 over square root of 2E. And now this is 0, 0, 2e, 0. Okay, so what does this say? This of course is the v that multiplies the creation operator. So the spin-up creation operator, the left-handed one, has this spin down, and the right-handed one, if it's spin down, has the thing in the spin up. It looks funny, but that's actually the way it is. Now let's see. This there's sort of two ways you can write these spinors, and I think the m plus p slash for u and the m minus p slash for the v's is the easiest way to do calculations. In particular, if we look at this calculation, then this is u dagger of p and s, gamma 0, u of p, and s prime. And so the two normalization factors give us 1 over 2 e plus m, and then we have alpha dagger of x. Let me just write it as alpha dagger for s. And then this thing is m plus p slash dagger, and then there's a gamma 0. The gamma 0, of course, is because u bar, by definition, is u dagger gamma 0. And we then have m plus p slash, and then we have alpha prime, the prime meaning that it's s prime as opposed to s. And you remember that gamma mu dagger gamma 0 is equal to gamma 0 gamma mu. The reason for this is that gamma 0 is Hermitian, being, I guess you can, well, here, let's just look at them for a moment. Gamma 0 is 0, 1, 1, 0, so that's Hermitian. Gamma, the vector gamma, this Pauli matrix, these are Hermitian, but there's a minus sign here, so they're anti-Hermitian. And on the other hand, gamma 0 commutes with gamma 0, obviously, but gamma I, the space index, anti-commutes with gamma I, so you get two minus signs, and that's why this works. So this equation can be rewritten as 1 over 2. Boy, I violated the de Blasio rule big time, didn't I? Sorry. It's not an English word. Well, I don't know. I mean, in my view, mathematics is the language of physics. And I resolved to follow your rule. It's just not me. All right, gamma 0, and then we have m plus p slash squared, and then alpha prime. So what we're going to do is we're going to evaluate this. Okay, so what is m plus p slash squared? Well, this is all right, m plus p squared is m squared. Now, p slash squared is p squared, and that's m squared. So we have a 2 there. And then you have a cross term, 2m p slash, and then alpha prime. Okay. And, all right, now, so what, and then there's a gamma 0, which I left out. That's that gamma 0. And, okay, so if we look at what's in here, let's just look at the gamma 0 p slash term. Well, then what we have is alpha dagger, 0, 1, 1, 0, 0, p sigma bar, 0. And now p sigma means in as much as it came from here, it's p0 sigma 0 minus p dot sigma. But this one is the opposite. It's p0 sigma 0 plus p dot sigma, because there are two minus signs, one from the bar and one from the Lorentz inner product. Anyway, this is then alpha prime, and so this is alpha dagger, p sigma bar 0, 0, p sigma, alpha prime. And now you see, because these spinors are the same, this thing actually simplifies. It becomes alpha dagger, p sigma bar plus p sigma, alpha, and that's just 2e alpha dagger alpha prime, which of course is delta SS prime. So there's a 2e. But there's also this term, 2m squared. And because this is a 2 vector, it's really effectively 4m squared. And so what we get then is that u bar of p and s, u of p and s prime, is alpha dagger 4m squared plus 4me alpha prime over 2e plus m. And this gives us 2m delta SS prime. So that's the inner product. And I think this shows you the utility of using this m plus p slash notation. It makes things somewhat simpler. All right, so if we now, maybe I'll start the calculation here. Now I want to compute the usual inner product, u dagger u. And so we have u dagger ps, u of ps prime. This is 1 over 2 e plus m alpha dagger. And now this is then m plus p slash dagger, m plus p slash alpha prime. And that's 1 over 2 e plus m. There's perhaps some typos. Alpha dagger. And now what we've got is m plus e gamma 0 plus p dot gamma. The p dot gamma comes in with a plus sign because it would have a minus sign because of p slash, but because of the adjoint, you have another minus sign on the space components. And then this one is m plus e gamma 0 minus p dot gamma. And then alpha prime. Well, if you work all that out, what you get is this factor 1 over 2 e plus m. And then you have alpha dagger, and then m plus e gamma 0 squared plus p vector squared alpha prime. Now you might say, why is it plus p vector squared? Well, p dot gamma times p dot gamma is minus p vector squared, and then there's another minus sign. Okay. Well, let me just give you what the answer is. It's now fairly straightforward. It's then u dagger ps, u of ps prime is 1 over 2 plus m, alpha dagger, it's then 2e squared, 2e squared, alpha prime. And this turns out to be 2e delta s, 2e, let us say, alpha dagger, alpha prime, which is 2e delta s, s prime. Okay. One can also show what the sum of UPS, U bar of P and S is. And this turns out, I'm going to skip the details. It turns out to be P slash plus M. And if we do instead the antiparticle spinors, PS, we get M minus P slash. So I really should have written that in plus P slash. Okay, now that's enough of the spinor algebra, I think, for now at least. Let me now go to charge conjugation, and once again I want to follow Weinberg a little more closely rather than Schwartz. So let us define charge conjugation this way. In fact, this is the point of view that Weinberg takes throughout his volume 1. He takes the particles to be the fundamental objects and the fields to be something that you invent so as to create a formalism that is Lorentz invariant, that has causality and locality and so forth. And so from that point of view then, instead of fooling around with the wave equation as the basic thing, we look at the creation and annihilation operators. So what this will be some phase alpha sub n times the creation operator, same momentum, same spin, but now it's the creation operator for the conjugate particle. So that's, of course, exactly what we mean by charge conjugation. And the problem with Schwartz's spinors is that he winds up flipping the spin, and that's just not right. Now, if we take the adjoint of this equation, and remember that C is unitary, then this is CA P S N. C inverse is alpha n star A of P S N C. All right. On the other hand, we also have the antiparticle. And how does that behave under charge conjugation? Well, it would be A dagger of P, S, and now the conjugate type, or kind, and now this is the phase factor for the conjugate type. And again, taking the adjoint and remembering that C is unitary, we get A. So we've got two different phases then. We have alpha sub n and we have alpha sub nc. And we want these phases to be such that the field behaves nicely under charge conjugation. And so let's see what happens then. In fact, what we will have then is C psi of x, C inverse, which we'll call psi conjugate of x, will be an integral dqp over 2 pi cubed, a sum on S, and now it'll be u of p and s, alpha n star, a p s n conjugate, e to the minus I px, plus v of p and s, alpha n c, a dagger of p s n, e to the I px. Okay, so what I've done here is I simply used these relations and assumed that this was an ordinary linear unitary operator. Okay, so now the question is, how are these things related to the anti-spinors? Because you see, what you would expect here is that if you have, let me make sure I've done this correctly, by the way.
So,
Is there a question?
yeah, lots of questions.
Either a question or a hunger pang. Let me get the candy in any case.
So,
Oh, and I have to give one to the faithful TA.
oh, thank you. So I'm gonna back up a little. You see, so Schwartz says that the spinors in a conjugate flip from particle to antiparticle, and their spin flips.
Yeah, he's wrong.
He's wrong.
Yeah,
Okay.
yeah.
So, okay, so then you're doing the conjugate up here on the top two. Should that be, is it NC to N? Or not?
Ah, yes, brilliant. Absolutely. Yes, thank you. And in fact, let's make well, I did it here, didn't I? Because this would be NC, yeah. Okay, you get another candy. All right. Now, let's see what's going on here. Well, maybe, all right, let me do it the logical way. First of all, let's recall that gamma 2, gamma mu star is equal to minus gamma mu gamma 2. Now, why is this? Well, all of the gamma mu are real except for gamma 2, which is imaginary. So if mu is 2, and this is clearly right with the minus sign because gamma 2 is imaginary. On the other hand, if mu is not equal to 2, then the gamma matrix is real, but it anti-commutes with gamma 2, so that gives you the minus sign. Okay. Now, what I'm going to compute is something that you might think is really pretty silly. Use gamma 2 on u star, and in fact it is slightly backwards. But, gamma 2 u star, so what is this? It's gamma 2 m plus p slash star, and then the two alphas, alpha of s, let us say. And then there's the normalization, square root of 2 e plus m. Okay, but now we can move the gamma 2 through, in other words, and flip it, so it's m plus p slash over the normalization, and then gamma 2 alpha of s, alpha of s. So the key thing is, what does gamma 2 do to this alpha of s? And here's what it does. Gamma 2, let us say alpha plus, alpha plus. So this is, gamma 2 is zeros, 0 minus I 0, 0 I minus I 0, zeros. And then up here we have 1, 0, 1, 0. And if we multiply that out, we get 0, I, 0, minus I. And this, you see, is I, beta plus, minus beta plus. So that means that gamma 2, U star of P plus is IV of P plus. So gamma 2 plus complex conjugation takes you from the spinor to the anti-spinor of the same spin, but with a factor I. And you can verify, in fact it's pretty clearly true, that U star P minus is IV P minus. Okay, now what about the anti-spinors? Gamma 2 V star of P and S. Well, this is gamma 2 M minus P slash star over the normalization. I'm just going to write the normalization as a square root. Beta of S minus beta of S. And once again, the gamma 2 comes through and removes the star, and so we have M with an accompanying, let's see, where did I write that? The gamma 2. Moving a gamma through a star gives you a minus sign. So instead of minus, we have M plus P slash. That's the sign of a spinor as opposed to an anti-spinor. Normalization, and now we have gamma 2 on beta of S minus beta of S. Okay, well let's consider the plus case. Then gamma 2 beta plus minus beta plus, this is zeros. 0 minus I, 0, 0 I minus I, 0, zeros. Oh, I didn't need that stroke there. And now beta plus is 0, 1, minus beta plus is 0, minus 1. So remember, when you go from spinors to minus spinors, you basically interchange the plus and minus, and you add an overall minus sign. And now what is this? Well, this turns out to be I0, I0, which is I, alpha plus, alpha plus. And so the lesson then is gamma 2, V star of P plus is IU of P plus. And gamma 2 V star of P minus is IU of P minus. Questions? All right. Okay. Now, you might say, why did I do gamma 2 U star? Why did I do that? Well, the reason is that that's what you'd expect from charge conjugation. But let me proceed in the logical way, namely that we have this expression here. So I'm now going to write U in terms of gamma 2 and V. And so what we have is gamma 2 U star of P and S is IV of P and S. Okay, well, complex conjugating the whole thing, we get gamma 2 star U of P and S is minus IV star of P and S. All right? And now, if we multiply from the left by gamma 2, what we have is minus gamma 2 squared, and that's plus 1. So we have U of P and S is I gamma 2 V star of P and S. Now let's see, did I screw that up? Because in my notes I have a minus sign, but it's easy enough to check. gamma 2 star, this is of course U. So in other words, going more slowly, we have minus gamma 2 U equals minus I B star. Multiply by gamma 2, you get A is equal to minus I gamma 2. Yeah, it is minus. Multiply by gamma 2, yes, minus I. All right, so what I had in the notes is right. So it's minus I. Okay, so speak up if you think I screwed up the sign. All right. Similarly, V of P and S. Well, all right, let's do this more slowly. What this says then is gamma 2U of P of S, the star, is IU of P and S. So that's gamma 2 star V of P and S is minus I U star of P and S. This is minus gamma 2 V of P and S is minus I U star of P and S. Multiply by gamma 2, we get 1, so V of P of S is minus I gamma 2 U star of P and S. All right. Now, what we have is something nice. Because if we come back to this equation, which arises from the basic definition of what we mean by charge conjugation, then we see that psi c is integral dqp over 2 pi q, sum on s, u of p and s is minus I gamma 2 v star. So this is minus I gamma 2 alpha n star v star of p and s, a of p s n c e to the minus I p dot x, and then plus v, and v is minus I gamma 2 u star. So this is minus I gamma 2 u star of p and s, and now this one is alpha sub nc, a dagger of p and s n e to the I px. Okay, so that's what psi conjugate is. Now, this thing here, okay, this combination of creation and annihilation operators and Fourier factors and phases, this thing is going to be simply related to psi if these phases are the same. Okay? Because if they are the same, then we can say that psi c is minus I gamma 2 I'm extemporaneous so much here that I've lost track of what the notes are. Let us just say alpha sub nc, and then integral dqp 2 pi q, and what we've got left then is a dagger of psn times u star, I should have done that, I should have put the u in front, and then plus v star of p and s, a of ps n sub c, and of course there's a phase factor, e, the phase factor on the a dagger is e to the I px And the phase factor on the A is e to the minus I px. Okay. All right, what is this thing here? This thing here, you see, is just a complex conjugate of the field. Okay, where's the field? And the field is on that front board, and you can verify that this is the complex conjugate. So this is equal to minus I gamma 2 alpha sub n c psi star of x. But if, only if, these things are the same. Alpha star n is alpha nc. So this is the requirement, and this requirement of phases then comes from causality, because if, and charge conjugation, but if the phases aren't the same, then you aren't going to get a psi star, and then the thing isn't going to anti-commute or commute, well in this case anti-commute, it's with psi at space-like separations. So what this says then is that the phase factor of the particle is the complex conjugate of the phase factor of the antiparticle under charge conjugation. So in other words, this very basic definition, alpha n star is alpha nc. Okay, now you might say, well, this is kind of weird. Why is it that the conjugate field is minus I gamma 2 a phase times the complex conjugate? Well, to show you that this makes perfect sense, let me go back to the basic Dirac equation of a particle of charge E and mass m interacting with an electromagnetic field. And I'm going to do it in a slightly better way than I did it last time. So let me maybe leave the rinse and variance and causality there, and I'll erase the rest of it. Oh, it's probably useful to leave the field on there also. Okay, so Dirac's equation is I d mu gamma mu minus E a mu gamma mu. So we could use slash anyway. Minus m psi of x equals 0. Okay. Now, suppose we complex conjugate this. Then we get 0 equals minus I d mu gamma mu star minus E a mu, the field is real, gamma mu star minus m psi star. And, well, remember that, all right, so what I'm going to do now is I'm going to insert 1 in the form minus gamma 2, gamma 2. So minus gamma 2, gamma 2, and I can multiply by gamma 2 and I still get 0, right? Okay. Now, what happens here? Well, as we've seen, gamma 2, gamma mu star is minus gamma mu gamma 2. Let me make sure I got that. If this is space, then just says the anti-commute. If it's not 2, I'm sorry. If mu is not equal to 2, this just says the anti-commute. If mu is 2, of course they do commute, but this thing is imaginary. So if we now multiply by gamma 2, we get gamma 2 squared. And if we multiply again by minus sign, we get a plus. And so we get minus gamma 2 gamma mu star gamma 2 is equal to minus gamma mu. So this operation here, gamma 2 minus gamma 2 on both sides of a gamma star gives us a minus gamma mu. So this thing is minus gamma mu times minus I, so that is I d mu gamma mu. But here, we're just flipping this to minus gamma mu, and then this becomes a plus. And now what we have is gamma 2 psi star. So in other words, if psi satisfies the Dirac equation for charge E and mass m, then gamma 2 psi star satisfies the Dirac equation for the opposite charge, same mass. Last time I told you that we had to assume that the sign of m doesn't matter. It doesn't matter. But this time we don't have to assume that. Okay. So that's why it is then that we expect that charge conjugation is something like a phase times gamma 2 times the complex conjugate of the field. And now we see that in order for this to satisfy Lorentz invariance and causality, although I haven't gone through the details there, but it's kind of apparent, at least intuitively. In other words, gamma 2 psi, or to put it differently, under charge conjugation, if the phases of the antiparticle weren't the complex conjugate of the phase of the particle, under charge conjugation, we get some object that wouldn't commute or wouldn't anti-commute in space-like separation to the psi, because it wouldn't be psi star, it'd be some funny thing. And the reason why this matters is that you see you'd have the positive frequency part with the negative frequency part, and then the negative frequency part with the positive frequency part, and these things just don't cancel unless the phase is right. All right, so I think that's enough for charge conjugation. So the bottom line, once again, is the charge conjugation phase factor of a particle is the complex conjugate of the charge conjugation phase factor, the antiparticle. And if you have, on the other hand, a field that is spin 1/2 but real, say a Majorana field, then the charge conjugation phase factor must be real, because the antiparticle is the same as the particle, so the anti-field is the same as the field, and consequently you have alpha n equals alpha n c star is the rule, but this is the same thing as alpha n star, so the phase has to be real for, let us say, a Majorana fermion. Because on the other hand, charge conjugation is not a very big deal on a field that's neutral, or a field that's self-conjugate, even more strongly than neutral. All right, now let me do parity. I should have been moving a little faster in this lecture. Parity, in some ways, is simpler. On the other hand, time reversal is completely puzzling and mystifying, and so I'm not going to do that today. And on Wednesday, I really want to get us to the point of starting QED, because we've been fooling around too long with these various other things. So how are we going to define parity? Well, let's once again take Weinberg's point of view. is a parity operator on A dagger of P and S and kind N or type N, P inverse, and it's some phase factor, A dagger, but now this is PP and S and N. And the complex conjugate then is, or the commission conjugate is P A of P S N. P inverse is alpha N star A of, and PPSN is just the image of the momentum under parity, and of course it flips space and not the time component. Now if we have the conjugate field, we would have P of A dagger PS N conjugate C inverse would be alphas of N conjugate A dagger of P on P S, I'll just say reflected as P, and then PA P S N C, C inverse is alpha N C star A of reflected momentum S and C. Spin doesn't get reflected because spin, of course, is an axial vector, R cross P essentially, and so you flip R, you flip P, nothing changes. Okay. Now, it will turn out that alpha NC has to be minus alpha N star in this case. And let me try to show you that.
Sorry. So your C's are supposed to be P's.
My what?
C's on the left-hand side.
Left-hand side. Oh, Jesus, yes. P's.
Okay.
Everybody's a P there. Two for, well, two, always for contributing you get two. Yeah. Okay, so what happens to P psi of X? In fact, let me write it this way, I'm going to just write it as X. Well, this will be an integral, of course, dqp, 2 pi q. I should have, in fact, maybe I should write it right under that. So let me, well, there's no space under that. So let's just say we go from there to there. And what we have then is a sum over spins, and then we have u of p and s, alpha n star, a of reflected momentum s n, e to the minus I px, plus v of p and s, alpha nc, a dagger of reflected p s n c, e to the I px. Okay. Big time typo here. All right, now what we can do is we can flip space momentum. If we flip space momentum, then this just goes to P, but then what we have is dqp, 2 pi q, sum on S, we have u of reflected momentum S, alpha n star, a of psn, e to the minus I, and now we need to reflect P, but that's the same as reflecting X. So this is e to the minus I p reflected X plus v of reflected P S alpha nc, a dagger ds nc e to the I p reflected X. Okay, so the reflected X that we have here is of course exactly what we want. We expect that, well, I didn't say it yet, did I? We expect that I somehow skipped that equation. We will expect that this thing will be some sort of a phase psi of reflected x. That's what we want parity to do to the field. And once again, our spinors are u of p and s is, of course, m plus p slash normalization factor alpha of s, and the v spinors are v of p and s, m minus p slash normalization beta minus beta of s. All right, now, oh, and when I say that, we could have a matrix here, and in fact, we'll want a gamma matrix. It'll be a gamma 0. Okay, well, let's compute gamma 0 on u. Gamma 0 u of p and s. Well, this is gamma 0 m plus p slash, and now we can put in two gamma zeros here because gamma 0 squared is 1. Normalization, alpha of s, alpha of s. Okay. Now, what happens here? Well, the gamma 0 comes through. It doesn't do anything to time, but it flips the sign of space. And it hits the gamma 0 and gives us 1. Okay. So this is equal to m plus pp slash gamma 0 alpha of s, alpha of s. Okay, now what is gamma 0 on these alpha of s's? Well, nothing much happens because gamma 0 is 0, 1, 1, 0, and this is alpha, alpha. So, of course, this is just alpha, alpha. So gamma 0 has no effect. So this is m plus pp slash alpha, alpha. Again, square root of normalization. And so what is this? This is just u of the reflected momentum and the same spin. Okay. But the antiparticles are different. For the antiparticles, we have gamma 0 v of p and s. This will be gamma 0 m minus p slash gamma 0 squared beta minus beta square root of normalization. This gamma 0 flips everything, so this becomes m minus pp slash. But now gamma 0 on beta beta, beta minus beta, you see, has a big effect. This becomes minus beta beta, so there's an overall minus sign. So this thing is equal to minus m plus reflected momentum slash normalization beta minus beta, or minus v of reflected momentum s. No, u. What am I saying? No, it was a typo. It's v. No, it's typo. Okay. So what has happened here? This thing has turned into then, or to put things differently, let's just summarize what we've just found. Namely that u of reflected momentum and s is gamma 0. This is gamma 0 u of p and s. And this one is minus gamma 0 V of P and of reflected P. Or I'm sorry, it's U of reflected P and S is gamma 0 U of P and S. V of reflected P and S is minus gamma 0 V of P and S. So that means then that the unitary parity transformation on psi turns it into a gamma 0 overall, p cubed p 2 pi cubed. Let us pull out the alpha n star. And then we'll have sum on S, U of P and S, A of P, S, and N, e to the minus I P reflected space, plus, now we have minus alpha NC. So it's minus V of P and S, alpha, well, I've pulled up. All right, it's alpha NC divided by alpha N star, because I pulled out an alpha N star. A dagger of PS NC e to the I P reflected X. Okay. So this is the same thing. This will be alpha N star gamma 0 psi of reflected X if this ratio is minus 1. So that means that the parity of a particle is minus the parity of the antiparticle. And that means that if the particle is self-conjugate, if it's a Majorana fermion, then the parity must be plus or minus I, it must be imaginary. All right, so I think that's the end, yes it is. So that's how one really should think, I think, about the spinors and parity and charge conjugation. Time reversal is much more puzzling. It's an anti-unitary, anti-linear transformation. And I find it hard to wrap my head around those two words. But I'll say a few, on Wednesday I'll say a few words about time reversal, a few more words about spin and statistics, and try to get us try either to start QED or to get us through chapter, what is the next chapter in Schwartz, 12 or something. Any questions?